Hi, welcome back. On today's lecture series, we are going to discuss about economical scheduling of thermal power plant without transmission losses. So, while doing the empathy, who feel this problem? Whether the grid operator or consumer or utility company or the environment. So here, the grid operator, it must meet load demand every second. It needs to the cheapest dispatch instantly. And the consumer, he pays every inefficiency. He want a reliable, affordable, and uninterruptible. And the utility company, the fuel cost is the single largest operating expenses, so it is an optimization. That is nothing but we have to increase the profit. And in the environment, inefficient scheduling, it gives excess fuel burn so that more emissions to the environment. And in the define stage, so how we have to allocate the total demand among all thermal generating units so that the total fuel cost it can be minimized and it can be subject to the power balance and unit limits. So no transmission losses, that means the losses can be neglected. So the constraint it should be the total generation which is equal to total demand because the losses is negligible. And each unit operates within minimum and maximum value. And the fuel cost curve, it should be a quadratic function of output and no inter-unit coupling through the network losses. And the cost function for each unit, the quadratic fuel cost curve, the F is nothing but in fuel cost and PA is nothing but ith bus power equations, which is equal to AI plus BI PI plus CI PI square rupees per hour. So this is nothing but in fuel cost equation. So AI, BI, CI are the coefficients of units. And PA is nothing but then real power output for ith bus. And the incremental fuel cost is the differentiation of fuel cost to I divided by dPi is equal to BI plus 2CI PI. So here the incremental fuel cost, it represents the slope of the curve and the cost of producing one more megawatt. So the equal incremental cost, it is the minimum total fuel cost for all committed units and it must operate at equal incremental cost. So the lambda value for all number of incremental cost should be equal. So the lambda is nothing but in system lambda, it is an incremental cost of supplying one additional megawatt to the system. Every unit it shares the load at same marginal cost. So this is a derivation using the Lagrange multiplier. The first one, the objective function, we have to know the objective of minimizing the value, and for equal constraints, we have to meet out the power demand, which is the and no losses. So that is what the generation is equal to demand power. And the Lagrangian formula, we have to use the Lagrangian formula and we have to differentiate and we have to set as 0 for incremental cost to fuel cost criterion. And for solving optimal dispatch, so express PI, real power for ith bus in terms of lambda. So BI plus 2CIPA is equal to lambda. So therefore, the real power for ith bus PA is equal to lambda minus BA divided by 2CI. So by substituting the value of lambda and the coefficient of BICI, we can able to determine the power generated from ith unit. And apply power balance equation, that is nothing but the generation which is equal to demand. And this is the formula to determine the lambda. The lambda is equal to maximum demand PD plus summation I is equal to 1, I equal to 1 to n, BA divided by 2 CI divided by 1 divided by 2 CI. So here we have to assume the lambda value and we have to compute the real power generation from the ith unit, like real power for unit 1, real power for unit 2, like P1, P2 for etc. for all units. And we have to check balance the equation like the total generation which is equal to demand or not. So based on that we can able to adjust the lambda. So here enforce the limit, whether it's within a limit or not. And the handling of a generator limit. If the generated power is less than minimum, we have to set as minimum and remove unit lambda iteration. And if the generated power is greater than the maximum value, we have to set the generated value as maximum value. So it should be operate within a limit. Okay. So here the few constraints have to be followed. And this is a 3-bus system. For each bus system, they are given the fuel cost A value and B value and for CA value. So the total demand of 800 megawatt for all combination of all 3 units. So for this, we have to determine the values like the lambda value, PG1, PG2, and the total power balance equation, cost, everything. So here we have to validate the optimal schedule by using the incremental fuel cost for unit 1, unit 2 and unit 3. So this is a real world applications, like it can be used for the energy management system like SCADA, supervisory control acquisition system, energy management systems, the platform with the economic dispatch algorithm for every 5 to 10 minutes in grid operations. And the electricity market, according to the ISO, like POSCO in India, use economic dispatch to clear day ahead and the real-time market. So this is the summary for the economic dispatch without transmission losses. We have to know the cost function and we have to draw the quadratic curve. And we have to note down the coefficient like A, B, C, and we have to do the optimally criterion. So this is an accurate challenge. If 2 units have identical cost coefficient B and C, what happens to the incremental fuel cost curve solution? Will there is a unique optimal solution or different one? If you know the answer, just you can put in the comment section. And this is for your understanding. Why is the equal incremental cost criterion a necessary but not sufficient condition for a global minimum? What additional check is required? And these are the few textbook and reference books for this topic. Thank you.